Hello there, ATS 114 TAs. Dr. Shragi here, and I am just walking you through Lab 10 for the lab this week. And I just wanted to first draw your attention to this set of questions associated with this set of plots here with this sort of idealized mid latitude cyclone. I'm going to zoom in on one of these cyclones here. What the first part of the question is asking you to do is to draw a standard weather symbol for winds or whatever at each of these four stations, A, B, C, and D, for each of the three plots below, which are each a different day. What it's asking them to do is draw like a little wind barb kind of thing here at each of these stations. And what you should do is make the winds pretty much parallel to the isobars, but kind of crossing the isobars from higher pressure towards lower pressure so the winds are spiraling in towards the wind. Remember, the little barb itself points upwind. The little flag that sticks off the side of the bar, don't worry about the wind speed in this particular problem. Now, once you have drawn those wind barbs at those four stations for the three times there, what you'll find is on the right side of this diagram here, there's these columns of station models. What they want you to notice is, see, here's one, there's another one, here's one. Okay, each one of these corresponds to either A or B or C or D. And so they just want you to go through and then realize, oh, I see, this one looks like, let's just say station A, and this one looks like station D, and this one looks like it's station C, and this is station B, or whatever the right answer is, okay? Anyway, that is not all that well explained as to what they're looking for in the actual handout there. Okay, after you do this kind of stuff here, then they start switching to a real world example. And most of these questions involve just reading something off the maps. Like I think this one here is a pretty good example of what we're talking about. It wants you to just kind of go through the map and talk about how much of the pressure changed at the storm's center. So they'll use the contours to determine what was roughly the pressure at the center of the cyclone at each of those times, and then just come up with the change in pressure. For what it's worth, by the way, don't have them answer question 6. This just isn't helpful at this time, and there's no particular reason to frustrate them. So anyway, there's a whole bunch of these questions about these weather maps, and I think most of the questions focus on one in particular. Let me see. I think it might be this one, where it's asking, for example, about the weather conditions before, ahead of, and behind the cold front. So you'll be comparing like what was the typical difference in temperature ahead of the cold front and behind the cold front, or was the difference in the dew point ahead of the cold front and behind the cold front. And it's just kind of helping the students get a sense of how big the changes in the weather are at these different locations. Now, a little bit of a tricky thing here, just because the students aren't familiar with the format of such a diagram before, are these meteograms. Real meteorologists do use meteograms quite a bit. They're just diagrams that have time on the x-axis and then weather observations at that station along the y-axis. And usually there's multiple y-axes because they plot lots of different types of data. I want to first draw your attention to the fact that this x-axis is kind of weird. See how these numbers down here? Like 9/0300, that's supposed to be on the 9th of November, I think it is, at 3 o'clock in the morning. So like this one is on the 10th of November at 3 o'clock in the morning, and this is on the 12th of November at midnight, and so on. There's about 4 days of data along that x-axis. I also want to draw your attention to the fact that there is 4 days of data on this plot. No meteorologist would ever have 4 days of data on a plot here. There's way too much information on this plot, but they're what we have to work with. I mean, normal meteograms would be like 12 hours or something like that. So what they're going to be doing here is they're reading this diagram and they're seeing that, like, for example, here's the trace of the pressure over that 4-day period, and here's the pressure scale. And there's scales, there's graphs of temperature and dew point. They both use this scale right here since they both have units of degrees Fahrenheit. And you'll notice that there is a little set of bars here. This is precipitation on this scale over here. Yeah, again, I don't like how small they made those. I mean, good grief. That actually is inches per hour. I mean, do we really think there's going to ever be 5 inches per hour of rain in one of these kind of events? No, of course not. You can see also that there's wind barbs here and so on. Anyway, so you're going to use these diagrams here to kind of come up with like things like how big of a temperature change was there, and so on. In particular, I believe what the book wants them to do is they're going to find frontal passages where, like, okay, right about here, there's a frontal passage. The pressure is lowest as a front goes by. It's higher ahead of the front in the warm air mass. It's higher behind the front in the cold air mass, but at the front itself, the pressure is relatively low. You can see in this case how the temperature kind of was trending down after the front went by. Right ahead of the front, there was this precipitation. There was a wind shift, etc. There was all kinds of good stuff here. Again, here kind of bites them again that there's so much data on these plots. they're going to have a hard time coming up with exactly what hour they think the cold front came through or the warm front came through on these plots, just because there's too much data on here. As long as they're within, like 6 hours or something, I would say that that's fine. I mean, on a finer plot where maybe this whole plot only had 6 hours or 12 hours of data, it'd be much easier to come up with exactly when the front came through, but we don't have that kind of information here. All right, so anyway, they would do answer a bunch of questions about this. Now, there's just one more thing I wanted to draw your attention to on this. Actually, I think I just went past it. There is a diagram on here where they're going to be finding advection. And we were talking about this at the meeting. You might remember that nobody except meteorologists love these plots where there are multiple sets of contours on the same plot. But actually, now you're going to find out how useful they are. Remember, this word advection has to do with when a property is being transported by the wind. Now, I mean, we have moisture advection and vorticity advection, and in this particular lab activity, we're talking about warm air and cold air advection. Warm air advection and cold air advection. So, on this plot right here, these solid contours are heights on the 850 millibar surface. You could think of them, of course, as something like isobars. And so the winds are going to basically be parallel to these isobars, something like this. Okay, they're going around this cyclone at 850 millibars there. Okay, if they don't like that, there's also wind barbs on there to help them get a sense as to which way the direction is and so on. Now look at these little dash contours. Now again, in the video I made for the students, I actually made one of these plots in color just to help. But okay, if you look at any given location on this diagram, let's just pick right here. Okay, if you look what's happening on that location, as the wind is blowing this way, see how it's bringing air that is cold towards a location that is warmer. We're transporting cold air towards a place that's warm. That's cold air advection. We are transporting cold air. In the same sense, like up here by Lake Superior, the winds are going this way. See how they're blowing across the the isotherms? They're bringing warm air towards a place that's currently cold. That's warm air advection. Now, you don't need to have fancy colors and stuff on the plot the way I do in the videos for the students, though, to understand how it's being done. Once you have this sort of plot with the two sets of contours on there, any place where there's these little diamonds, like here, see how the different contour lines, when they cross, they sometimes make these little diamonds? These little diamonds are called solenoids. And solenoids tell you that there is some kind of advection going on. In this case, it's temperature advection. So any place you see where the two sets of contour lines are making little cross shapes like that to make little diamonds, then you know that there's some kind of advection, either, in this case, because the contours are isotherms, then it's temperature advection. You're either having warm air advection or cold air advection. And then you can just use your analysis of what kind of winds are blowing, okay, the winds that are coming towards this location are bringing colder air. That's cold air advection. And then over here, this is warm air advection and so on. So you end up identifying in the diagram, in the activity, that like there's a area of cold air advection over here. The abbreviation for cold air advection is CAA. And there's an area of warm air advection over here. We call that warm WAA. Again, a professional meteorologist would really get fussy as exactly where to make those areas, but broadly, these are going to help them understand areas of cold air advection and warm air advection and how they could infer them from a map with two sets of contours. All right, make sure you use the rubric. There's a couple of questions I don't see any purpose of them answering, especially the last. I don't think they answer any of the review sections. Those questions seem much too broad for the purposes of our lab. I don't think they answer questions 26 and 27 either. Anyway, good luck with this lab. Let me know if you have any questions, and thanks for all you do.